Alright, I thought I'd make a short video for you guys to try to give you a couple more examples on strong induction from the textbook. And so here's just a brief, reminder. Strong induction goes like this. We suppose we need to show P of 1 is true, if we can do that, and if we can show that whenever P1 through Pk are all true, that implies that Pk plus 1 is true. If you can achieve 1 and 2 in an argument, then that means that for all n in the natural numbers, P of n is true, because these two assumptions prove to show that the inductive set is the whole natural numbers. Of course, you can also start strong induction somewhere other than 1, like you could start it at 0 or 3 or 47, whatever. And of course, you could also do it backwards, like I did in the notes. I'm trying to emphasize the importance of assuming the truth of the proposition as a ground. That's the context in which we have to prove the implication. True antecedent. All right, let's see here. So, example 1. Let's define this sequence a sub n by a recursive rule. We'll make a1 be 1, a2 be 3, and a sub n be 2 times a sub n minus 1 minus a sub n minus 2. So something like this, probably weak induction, isn't going to work on, because it doesn't involve just the interplay between the nth and the n plus 1th, or, well, in this case, the n minus 1th. It depends on 2 steps back, right? So probably strong induction is something we're going to need to use to prove something like this. All right, so this is the rule, though, for n greater than or equal to 3. The claim, and we're going to prove this by induction, is that a sub n is 2 sub n minus 1 for all n in the natural numbers. All right, so we start out by noticing that 1 is true. And then, then we go ahead and notice that, suppose Pn is true for n equals 1 to k. I'm going to show you what goes wrong with doing that. So, actually, I'm not, well, let me see here. Actually, I added an additional assumption that, you'll see why we need to add this assumption. Suppose k is greater than or equal to 2. Okay? The reason we need to do that is, as soon as you look at what you want to show for the, for k plus 1 being true, you're up here, up against a sub k plus 1, and that relates to this guy and that guy. But, alright, so if k plus 1, let's see here, if, how to say this, if n is equal to k minus 1, well, it could be that that n is less than 1, right? But we don't have a definition for a sub 0, right? Like that's not even a thing. So we can't even really compute this unless we already know that k is greater than or equal to 2. So we have to make that assumption here. So notice that if n is equal to k minus 1, it could be, I just said that, sorry. So we need to treat that case separately. All right, so assuming that k is greater than or equal to 2, we can meaningfully calculate 2a sub k minus a sub k minus 1. By the strong induction hypothesis, which I should really comment over here, but I made this stupid comment so I couldn't fit it in. 2 times 2k minus 1 for that, and 2 times k minus 1 for that. But then I do algebra, right? And fine, I'm feeling guilty. This step going on, come on, marker, work. Going from here to here, we used the induction hypothesis, right? We had to use it not just for k, though, we had to use it for k minus 1 as well, right? And because you need to use it for k and for k minus 1, I can't have k equals to 1, because that would have me giving, that would be a sub 0, and that's not even defined, right? So when I'm using the recursive formula, I have to have k greater than or equal to 2 for this argument to make sense. So there we go. And then algebra gives us this, which then gives us this, which then gives us what we want, namely that a sub k plus 1 is twice k plus 1 minus 1. That's the induction claim. Thus, for k greater than or equal to 2, we find that P1 and P2 and Pk true implies that Pk plus 1 is true. All right. Notice the very important introduction of the word true there. That was to be assumed before, but I don't think I emphasized it, perhaps. I don't know. Maybe I emphasized it, maybe I didn't. I guess we can all review the tapes. But, so notice that P2 is also true, of course, because A sub 2 is this. And so we've noticed what we can do here. If k equals to 1, then P1 true implies that k plus 1 is true because k plus 1 is 2 in that case. So we do have the necessary implication of P1 true implies P2 true in the special case that k plus 1 happens to be 2. On the other hand, if k plus 1 happens to be greater than or equal to, if k happens to be greater than or equal to 2, which is to say that k plus 1 is greater than or equal to 3, then we can use the argument that was up here, and we also get that implication that, sorry, I seem to have an errant mark there. Let me fix that. Excuse me. So therefore, by strong induction, we find that a sub n is 2n minus 1 for all n. All right. So again, we had to separate out that case because the recursive formula puts us back at a sub 0 where that wasn't even defined. So, you know, if the structure of the argument is like not just 2 steps back but 3 steps back, then probably you're going to have to separate out even more base cases to take care of the interplay of levels in the argument. Okay, here's another one. A sub n recursively defined by this. A1 is 1, A2 is 4, A sub n is 2a sub n minus 1 minus a n minus 1 plus 2. All right, n greater than or equal to 3. That's the claim is that a sub n is actually equal to n squared for all n in natural numbers. We're going to call that Pn. So P1 and P2 are clearly true because 1 squared is 1 and 2 squared is 4. All right. So then we'll suppose inductively that P1 through Pk is true. All right. Notice that in the case that k equals 1, then k plus 1 is 2, and there that's true. So we have the implication in the case k is equal to 1. So we can then consider k greater than or equal to 2. All right. I could have used the same format in the last example, but I wanted to show you the process of discovery. So suppose k is greater than or equal to 2. Then, assuming P1 through Pk is true, we can consider a sub k plus 1. And a sub k plus 1 by the recursive rule is this, plus 2. Little comment here, notice that k greater than or equal to 2, thus k plus 1 is greater than or equal to 3, thus if n is equal to k plus 1, it's greater than or equal to 3, and we're within the scope of the definition, of the recursive definition for a sub n, which was given up here. Notice the fine print, n greater than or equal to 3. We've met that mark with our k plus 1 being n and being greater than or equal to 3 in this argument down here. All right, so since we can do that, we're within our rights to write this down, and then this is just a simplification. The ones cancel, and 1 minus 2 is minus 1, so I have a sub k minus 1. And by the induction hypothesis, that's 2k squared minus k minus 1 squared plus 2. Then I do algebra, square that out, cancel some stuff, and then notice that factors to k plus 1 squared. But hey, that's exactly what we wanted to prove, that a sub k plus 1 is k plus 1 squared. Therefore, pk plus 1 is true for k greater than or equal to 2. Hence, Pn is true for all n by strong induction. There you go. That's a pretty typical problem that is, I guess that's about the simplest strong induction can get, when you just have like one base case. And this one's also kind of simple. Kind of disappointing the book doesn't have a strong induction example that's got like a lot more base cases. I guess we kind of saw that in class with the one we worked, which was the other example from the book. But anyway, here it is. So, third and final example here before I talk about your homework. If r is a real number with r non-negative, and if we assume that r plus 1 over r is an integer, then the claim is that r to the n plus 1 over r to the n is an integer for all n in the natural numbers. All right, for all positive integers. So here we go. First of all, notice that P1 is true because if this is an integer, then of course r to the 1 over r to the 1 is equal to r plus 1 over r as an integer. My apology for the wind. I'm outside, and it's kind of pleasant, actually. A little bit windy. Hope the wind noise isn't too bad here. Suppose inductively that... Oh, I probably should actually write n there, huh? N. There we go. Suppose that r to the n plus 1 over r to the n is an integer for every n between 1 and k. Alright, this is a strong induction proof. So we assume all those cases. Consider then, and this is just a sneaky, sneaky algebra step, that if we do r to the k plus 1 over r to the k plus 1, we can rewrite that as this plus that times this plus that. If we multiply that out, that gets us the r to the k plus 1. This times that gets us the 1 over r to the k plus 1. But in addition, we're adding a r to the k minus 1 from this outer product here, which we subtract over here to be fair. And also the inner product, this times that, gives us that 1 over r to the k minus 1. So we're subtracting that. So we've just added 0 in a kind of funky way. And then, by the induction hypothesis, we know that that's an integer, that's an integer, that's an integer, right? Because we're looking at either the k case, or k equals 1, or k minus 1, all assumed to be true by the strong induction hypothesis. But, of course, the product and difference of integers is integers, therefore r to the k plus 1 over 1 to the r k plus 1 is an integer again. Therefore, we can conclude by strong induction that r to the n over 1 over r to the n is an integer for all n and n. So there you go. All right. So that's 3 more examples. Again, sorry they're not in my notes. Perhaps they will be once I get a second here to type them up, but haven't done that yet. Hopefully we'll be editing the chapter on induction here today. But I wanted to get this video out to you now since you might be working on your homework. So just a comment about problem 50. One of you guys asked me about, like, what does the notation mean? So I thought I would just take a second here to try to unwrap it for you, because you might not have ever seen product notation before. It's pretty rare in the undergraduate mathematics curriculum. It doesn't come up much, but this is how it goes. So we define it recursively. It's given in the problem statement. It's like the product from 1 to 3. We do the third factor times the product from 1 to 2, and then recursively the second product times the product from 1 to 1, but then by definition the product from 1 to 1 is just f sub 1. So this is just a precise notation for f1 times f2 times f3, right? And if you continue down this path, right, the product from 1 to n is f1, f2, dot, 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 fn. Now, maybe you never really thought much about this, but this dot, 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 dot lacks a certain amount of rigor. If you want to prove something precisely about a product of n-fold things, well, it is recursively defined in terms of this n-fold product, and as such we can give more rigorous arguments using the recursive definition and the technique of induction. In fact, the proof that I put on the quiz last week, we also could have done more rigorously using a summation notation, but I didn't put that on you because we use a mix of the plus dot 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 versus the summation notation, and so anyway, I'm just saying you could reformulate the proof from the last quiz in a slightly more rigorous way using the careful recursive definition of the finite sum. So anyway, I just wanted to look at the claim of problem 50 in the case of 3, just to make sure you understand why it's true. This is not a proof, and this doesn't have to be part of a proof. In fact, if this is part of your proof, you're probably doing it wrong. So this is just for the sake of us understanding what the problem's asking, okay? So I equals 1 to 3, the product I equals 1 to 3 of f sub I is the derivative of this product, right? Well, the triple product rule, which is just coming from the product rule applied twice, actually, brings us to this. So we've got the first one differentiated, the second one differentiated, the third one differentiated, times the product of the remaining two, which are, of course, not differentiated. The trick here, in terms of creating a formula, is to notice that we can rewrite the products of the undifferentiated ones as the product of all of them divided by the one which was differentiated, all right? And then so I can repackage that as a sum I equals 1 to 3 of dfi dx f1, f2, f3 divided by f sub I, which I can rewrite in product notation as the sum I equals 1 to 3 dfi dx 1 over f sub I product k equals 1 to n of f sub k, right, where n equals to 3, of course. At this point, I looked at the problem again. I was like, uh-oh, I switched the meaning of I and k, but this gives me a chance to talk to you guys about something, which is these are dummy variables of summation and product, and you can change the letters, and the math stays the same. So I just changed this I to a k, and I changed the k to an I, and nothing has changed. These are the same expression in terms of its content logically. So anyway, I hope that helps you understand what the notation means in problem 50. Problem 49 also is like small comment. If you didn't know already, this parentheses notation means n-fold differentiation, right? Which technically means derivative of the n minus 1th one. To be more precise, the nth derivative is defined to be the derivative of the n minus 1th derivative for n in the natural numbers, with the understanding that the 0th case is just the function itself, all right? So that's the notation which is used in problem 49. I didn't explain that in problem 49 because it's standard calculus. And then, finally, a rather large hint for problem 45, which one of you asked me about. And I'm not saying this is the only way to do it, but it's the way that I thought to do it. You're supposed to prove by induction that the sum of the interior angles of an n-sided polygon is, n minus 2 times pi, where we're assuming, of course, n is greater than or equal to 3. I don't know what a two-sided polygon looks like, right? Well, I guess it still makes sense in some sense, right? If n equals to 2, this is 0. Maybe that makes sense. There is no interior angle to a two-sided polygon, right? What's a two-sided polygon? But a three-sided polygon is a triangle, and we know that for Euclidean space, which we're assuming we're in, the sum of the interior angles is pi, all right? So suppose inductively it's true for an n-sided polygon, and with n greater than or equal to 3, and consider an n plus 1-sided polygon, all right? Well, if you think about that, you could, make a picture kind of sort of like this, where you've got the n plus 1 vertices, right? N plus 1 vertices, and I just enumerate them, starting, like here's 1. My numbering's kind of weird, but I just numbered them like this: 1, 2, 3, 4, all the way out to n. Here's the n plus 1th vertex, which I've just put the angle alpha there, all right? So what I decided to do was to cut this n plus 1-sided polygon into 2 pieces, right? And this makes sense because it's convex. I'm not going to really prove that. I'm going to use some geometric intuition in this proof. So if that's a bother to you, then don't do this homework problem, because this is a geometric homework problem, and it's going to require some amount of geometric reasoning. But anyway, so here, this is a triangle, of course, because we've got 3 sides, and I've just connected two vertices which are separated by one other vertex, right, like that. And if I do that, that means that what's left over is, again, an n polygon with n vertices, right? So I can apply the induction hypothesis to that to know that there's, n minus 2 times pi, sum of the interior angles here, which I've labeled theta 1 plus theta 2 plus dot 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 plus theta n. On the other hand, of course, I know that alpha plus beta plus gamma is equal to pi, because these are the interior angles of a triangle, right? So there's that, all right? And then if you put these two things together, it's not hard to finish the argument. So the sum of the interior angles in the n plus 1-sided polygon is, well, how to calculate that? So first of all, we know this is true by the induction hypothesis, and we know that's true because it's a triangle. And if I add those equations above, this is a proof sketch. It's not quite, yet I make this. You can improve this a little bit with some words and stuff. And it's not quite a correct solution yet. It's just a work in progress. Sorry, guys. Then if you add those two equations above, then I have the sum of all these things, which is exactly like the n plus 1th interior angle, the second interior angle, the third interior angle, the first interior angle. The sum of all the angles is, in fact, n plus 1 minus 2 times pi. And if we go back, you can see geometrically, you can see what I'm saying isn't unreasonable. Like gamma plus theta 2 is the interior angle of the n plus 1 polygon, and theta 1 plus beta is the interior angle for the n plus 1 gon. And of course, alpha, as it happens, is the interior angle at the n plus 1th vertex. So I suppose I probably could clarify the proof a little bit if I was perhaps a little bit more systematic in my enumeration of the vertices or something. I suspect there's other ways to prove this problem in terms of like just dividing it up into triangles or something. But this is how I saw it today. So anyway, thanks guys. Have a good weekend.